Hello class, welcome to lecture 6 of our course. In this lecture we'll be discussing linear momentum. First we'll introduce linear momentum and talk about it conceptually. We'll move on to impulse, and finally we're going to talk about the first conservation principle in this class. That's the conservation of linear momentum. So let's go ahead and get started. Momentum, well, linear momentum. And let me this word linear, that's to delineate this momentum from another type of momentum associated with the other type of motion, which is rotation. This momentum is the momentum associated with translation. So we talked about translation in the previous lecture. Translation is motion through space along a path. And so this is the momentum associated with translation, linear momentum. But what momentum is, it's defined as the product of an object's mass and its velocity. Right? And we use the variable p to represent linear momentum. And so momentum is a vector quantity and it's equal to the product of an object's mass and velocity. All right, so that tells us that mass doesn't have a direction. It's not a vector. That's what we call scalar. But velocity is a vector, and because both sides of the equation can be equivalent, this equation tells us that our momentum vector has to point in the same direction as the velocity vector. So if an object of mass m has a velocity in this direction, then that object has a momentum equal to the same direction, that's equal to m times v. That has to point in the same direction as the velocity. So whatever direction the object is moving, that's the direction that its momentum is in. Now you might have heard the term momentum used colloquially in speech before. Oftentimes it's used maybe in sports. You've heard it. Like if a team has the momentum, right? Or there's been a swing in the momentum. One team is doing well, now the other team is doing well. So we tend to think of momentum as something's on a roll, right? It's going and it's going to keep on going. Well, that's kind of tied into what we refer to as momentum in physics. If an object has momentum, it is moving, has a velocity, and it doesn't want to stop moving because it has inertia, mass. So you could think of momentum as that, well, how much is it moving and how much does it not want to change how it's moving? So it is associated with motion, and it is kind of a way to quantify the inertia and the motion at the same time, because it includes the inertial term, the mass, and the motion, the velocity. And so if an object has a lot of momentum, then it's going to be hard to stop, right? Because it's either moving very fast, or it has a large mass, or both, right? So because it's the product of mass and velocity, two objects can have the same momentum while having different masses and velocity. For example, a car could have a velocity and a mass, where a bullet could have much larger velocity and a smaller mass, but they could have the same momentum. The momentum of the car could equal the momentum of the bullet. The car having a much larger mass and smaller velocity could equal the product of the small mass with the larger velocity of the bullet. So because it's the product of mass and velocity, you can have two objects with different masses and velocities, but they're still the same momentum. I'm saying they're in the same direction. Obviously, if they're in opposite directions, they can have the same magnitude of momentum, but opposite directions. Alright, so it's easy to find the momentum of an object. You just multiply its mass by its velocity. Right? And so we conceptually can think about this where a ping pong ball, right, has a very small mass. And so if a ping pong ball is coming at you with a particular velocity, you don't get that concerned, right? Because you know it's going to hit you and just drop, because it's, even though it's moving, it has such a small mass that you intuitively know from living in this world that it's just going to hit you and bounce off of you harmlessly, because it has little momentum. You might not be thinking it has little momentum, but you know that from experience. On the other hand, if a baseball is coming at your chest, say with the same velocity as the ping pong ball, you get a little bit more concerned, right? It's like, this is going to hurt. Like, when it hits me, it's going to hurt. Why? Well, the baseball is more massive, right? It has more momentum. It's moving at the same velocity as the ping pong ball. Then the momentum of the baseball will be larger than the momentum of the ping pong ball. Just by the virtue of the mass of the baseball being larger if you're moving at the same velocity. And so that baseball wants to keep on moving more than the ping pong ball because it has a higher mass, it has more momentum. And so in order to stop its motion, it takes more force. And that force, if it hits you in the chest, is exerted on the ball by your chest. And if your chest is exerting a force on the baseball, then Newton's third law tells us that baseball is exerting a force on you, and that's what hurts, right? So we already have an intuitive sense of momentum in interacting with the physical world. Like if something's coming at us that has a lot of momentum, we get concerned, right? Because it's going to hit us, it's going to hurt. Right? You can have two objects traveling at the same speed, the ping pong ball or a tractor trailer, right? If they're moving at the same speed, that tractor trailer has way more momentum than the ping pong ball. Why? Because it's so much more massive. Right? That tractor trailer, you're going to have a really hard time stopping that tractor trailer. You're not going to. Where the ping pong ball, it's easy, right? Because it's a very tiny mass. But you can have a really tiny mass, say like a slug of a bullet, but a really large velocity that gives it a lot of momentum. Right? So it's that product of mass and velocity that yields momentum. And like I said, momentum is kind of a way of quantifying how much something wants to keep going. It's the inertia multiplied by the velocity. You know, with a lot of momentum, the object is going to take a lot of convincing to change its motion if it has a lot of momentum. And so that brings us to impulse. So impulse is what changes momentum. If you want to change the momentum of an object, you got to exert an impulse on it. The impulse is the change in momentum of an object. So we use, for impulse, I've traditionally used the letter J. It's a vector equals change in momentum. Okay? It's change in momentum. And moving forward, the textbook boldfaces vectors. But it's hard to boldface variables when drawn on a board. So another convention of identifying vectors is using an arrow. And so that's what we're going to do from here on out. You put an arrow above the variable, that denotes that it's a vector quantity. So impulse, J, is a vector quantity, and it's equal to the change in momentum of an object. And so whatever direction, say if the initial momentum of an object is in that direction, and the final momentum of an object is in this direction, then the change in momentum is equal to this vector right here, right? Oh, change in momentum is equal to this vector right here. Right? So if that's a change in momentum, that means the impulse, that's the same as the impulse. The impulse points in that same direction. Now what is impulse? It's a change in momentum. I know, but that's not saying that much, right? There has to be more to it. Like say, oh, there is an impulse and the object's momentum changed. No, what we think, impulse has to be defined by something more than just change in momentum. How do you quantify what impulse is? Well, to answer that question, we're going to look at Newton's second law. So the net force being a vector, so I'm going to draw an arrow above it, is equal to mass of the object times the acceleration that the object experiences. Now if we rewrite acceleration as change in velocity, now velocity being a vector has the arrow above it, over change in time, now we can multiply both sides by delta t. Okay? Now, if we assume that the mass of the object remains constant, which in reality that's not always the case. Say like with a rocket that's launched to go into space, as it travels, its mass doesn't remain the same because it burns fuel. So as it empties its fuel tank, it changes its mass. But right now, we're going to assume that the mass stays the same. So if the mass stays the same and it experiences a change in velocity, then that means that object is experiencing a change in momentum. Because mass times velocity is momentum. We could rewrite this as mass times v final minus v initial. And if we distribute the mass, we get mass times v final minus mass times v initial. And this is just final momentum minus initial momentum, which is change in momentum. Right? So this is change in momentum. That makes this term, the net force applied, multiplied by the amount of time during which the velocity changes, that makes that equal to impulse. That's what impulse is defined as. It's a net force applied through some time, delta t, that causes a change in momentum. So that is impulse. It's force multiplied by time. Now, the force isn't always the same value during that time interval. So what we do is we use the average force. Okay? But let me just say, so impulse, okay? Or I could say change in object's momentum of object defined as F net times delta t. So it's some average net force applied for some time. Okay? And it's a vector quantity, it points in the same direction as wherever the change in momentum is. So if there's an impulse in that direction, that means that there's going to be a change in momentum in that direction. And the impulse, the direction of the impulse is dictated by the direction of the net force. Right? So impulse because time is not a vector, only force is a vector, so the impulse is in whatever direction that the net force is in. So let's say, for example, a baseball. A baseball is coming in, it has a mass and an initial velocity. And so its momentum is that value. Okay? Let's say it's negative, right? So let's say this is the positive direction. Let me erase this. let's say this is the positive x direction. So this baseball originally has a negative momentum. Now a bat comes in contact with this baseball, and while in contact with the bat exerts a force on the baseball. Now that force isn't the same all the time. If we would plot that force as a function of time, right? So this is delta t. This is the time interval in which the force is exerted on the baseball. So this is the time interval in which the bat and the baseball are in contact with each other. So as the baseball begins to come in contact with the bat, the force becomes non-zero and it increases. It's at a maximum at the midpoint, and then the force begins to decrease until the baseball and the bat are no longer in contact. Right? So that's how the force. So we just find the average force. We can find the average force. So find what would be the average force if we can boil this varying force of time down to one force of constant value that's applied for that entire time interval. That's what we're going to call the average force. So this bat exerts some average force on the baseball while they're in contact, and as a result, the baseball is sent in this direction. So the baseball, let's say it's even moving at the same speed. So the magnitude of V initial is equal to the magnitude of V final. We're moving at the same speed, but they have different velocities, right? Because V initial is negative, V final is positive. So their change in momentum is equal to the final momentum minus the initial momentum. And that's basically going to be 2. Well, let's there. So final momentum is m v final minus m v initial. Okay. V initial is a negative, so if we make this a negative, we drop the vector signs and give them their actual arithmetic sign. So v final is positive, so we'll write that as a positive. Minus v initial is negative, so we'll write that as a negative. See, those negatives cancel out. We get, and because v final and v initial have the same magnitude, I can write this as 2 and v initial. And that's our change in momentum. And so the average force times delta t. And this is a positive, right? This comes out positive. So we see the change in momentum is a positive. So the change in momentum is positive in that direction, equals 2 mvi. Alright, so we can find out what the average force of the baseball exerted, so the bat exerted on the baseball, if we know how long the bat and the baseball are in contact with each other. The average force is equal to 2 mvi, the velocity which the baseball is coming in, divided by delta t. Now the baseball doesn't have to leave with the same velocity, it will leave with a greater velocity, right? Or a smaller velocity. In this case, we just assume that it leaves with the same speed as it came in with. So we could find the average force the bat exerts on the object. So because impulse is the product of force and time, there's a trade-off there as well. In order for an object's momentum to change by a certain amount, it needs a certain impulse. Now that impulse can be provided by a large force over a short period of time, a medium force over a medium period of time, or a small force over a large period of time. Because it's the product of force and time, there's a trade-off. And a good example of that is with an egg. Right? If you have an egg that you drop So if you drop an egg, the egg begins to accelerate. Right before it hits the ground, that egg has some velocity v. Okay? And it has a mass m. And so it has some initial momentum p. Whenever that egg hits the ground, it comes to a rest. Let's say downward is positive y direction. It comes to a rest once it hits the ground. So here, once it hits the ground, it comes to rest, v final is equal to 0. So final momentum is equal to 0. So the change in momentum that this egg experiences is equal to p final minus p initial, which is 0, minus m v initial. We're saying down is positive, so I'm going to make this drop the vector sign and make it positive. But this negative sign is still here because it's minus p initial. So I'm minusing the positive. So I get negative mv initial. That's the change in momentum. The change in momentum is in this direction. Right? Which makes sense because if the initial momentum is downward, in order to come to 0, the change has to be upward to cancel that out to bring it to 0. So that's a change in momentum. Now that must equal the impulse, right? So the average force exerted on that egg multiplied by the time is equal to that change in momentum. So the question is how long does it take for that egg's momentum to change? Does the egg slow down gradually, or does it come to a stop suddenly? It comes to a stop suddenly. So the amount of time that its momentum changes, the time interval in which the egg's momentum changes as it comes to a rest once it hits the ground, is very small. It's very small. And so this time is very small. So as a result, there must be a large average force exerted on the egg in order to generate the necessary impulse to change its momentum. And what happens? That force breaks the egg, right? Humpty Dumpty is in pieces. And it's a mess. It breaks the egg. Is there a way that we can drop an egg, have it come to rest without it breaking? Well, yeah. We have to reduce the force that's exerted on the egg to bring it to rest, to accelerate it to rest. How do we reduce the force? Well, what we can do is we can increase the time. So how can we have it, so we have another scenario where a has a velocity downward, and we bring it to a rest, but it stays intact? Well, what if the surface that it's coming in contact with can give? Like it's a sheet or a pillow. That means that the egg comes in contact with the surface. The surface can then exert a force upward that's much smaller because it's slowing down over a longer period of time. So the force required to generate the impulse is smaller because it acts on the egg over a larger period of time. So we make the time bigger, we get the same impulse, the same change in momentum, right? The egg has a positive momentum downward, then it has zero momentum, so we have the same change in momentum. However, the force required to bring about that change in momentum is reduced because we increase the time during which that force is applied. So if we have more time for the force to act on the object to bring it to rest, or to change its momentum, in this case bring it to rest, then the force, the average force required is smaller. So that's how you can drop an egg on a pillow and it won't break, or drop it on a sheet and it won't break. It's like a tightrope walker or a trapeze artists swing, they put a big net underneath them. Why? Because if they fall, they hit the net can exert a force on them through a couple seconds, right? And bring them to a rest. So in order to change their momentum from a non-zero momentum as they move downward to a zero momentum as they come to rest, the force upward on them is smaller because it's applied through a larger period of time because the net gives. Where if they were to hit the floor, right, if they have a non-zero momentum, zero momentum. That change in momentum occurs over a very, very small time interval. And it's because that change in momentum occurs over a very small time interval, the force required is large enough to cause significant trauma to the body, right? Break bones and usually potentially cause death. We also use this same principle to mitigate injury during a car accident, right? We have airbags. Why do we have airbags? Well, if you don't have an airbag and you're driving, say at 35 miles per hour, and you hit something and you come to a stop, right, very quickly. Now your body has a non-zero momentum as you're moving. Now your body has zero momentum, you come to a rest. In order to have that change in momentum, your body has to experience an impulse. A force multiplied by a distance, by a time. And if you come to a stop very abruptly, then that time interval, which that force is applied, is small, so the force has to be large. So you get this very large force on your seatbelt, right? It exerts a huge force on your chest. Your head goes flying forward. Your head hits the steering wheel, and so the steering wheel exerts a really large force on your head to bring it to rest. So you get your body is subjected to these large forces applied over a short period of time to bring it to rest. However, if an airbag deploys, it comes in contact with your face, and then as you move forward, it's pushing against you for a longer period of time. If you could just increase the amount of time over which your change in momentum occurs by just fractions of a second, you can reduce the total force that you're subjected to. So the airbag is in contact with you, pushing against you for a longer period of time, allowing your momentum to change over a longer period of time, reducing the force required to generate the requisite impulse. Reducing the force is the name of the game, because the larger the force, the greater the trauma. And so if you can increase the time in which the body comes to a rest, you decrease the force. And that's exactly what an airbag does. It tries to, it pushes against the body for a longer period of time. Where that steering wheel, you hit that steering wheel, right? That steering wheel exerts a force against you for a very short period of time. Where as your head moves forward, the airbag deploys, and it pushes against your head for a non-trivial, maybe several fractions of a second, and allows you to come to a rest over more time. Therefore, there's a smaller impulse, smaller force required. Right? Same thing with helmets. Helmets have cushioning, right, that can give. So if you have a bike helmet and if you hit the ground, imagine your head falling, hitting the concrete. Your head comes to a rest quickly over a short period of time. So that quick change in momentum requires a large force, which causes trauma to the brain. However, if you have a helmet, which as your helmet hits, it provides some give, and it allows your head to come to a stop over a slightly longer period of time instead of just so abruptly. Just increases just a little bit. That decreases the force required. It decreases the trauma. So whenever we're trying to protect human bodies from impacts, we use this idea of impulse, and how impulse is the product of force and time. And as long as we can increase the time over which the body comes to a stop, we can decrease the force. That's also why cars are designed for the front ends to crumple up because as they crumple up, they absorb energy. We'll talk about energy in the next lecture. But it allows the car to come to rest over a longer period of time. The car's not really what's important, it's the bodies inside the car. They can come to rest over a longer period of time. That's reducing the required force. So impulse, this is called the impulse momentum theorem. That impulse. So now I'm writing average because this is the average force, because like I said, it's not the force that's exerted throughout the whole time interval, it's just the average force exerted throughout the time interval. This is the impulse momentum theorem. Impulse is equal to change in momentum. And so you can kind of rewrite this another way and see that the average force exerted on an object is equal to the rate of change of the momentum. If the rate of change of momentum is very large, there's a change of momentum over a short period of time, there's a large force. If the rate of change of momentum is small, there's a change of momentum over a long period of time, this number is going to be smaller, so the average force required is going to be smaller. So the average force required is equal to the rate of change of the object's momentum. Alright, so it's all about increasing the time. You increase the time, you decrease the force required. Right? If that time is very short, then the force required is going to be very long. Alright, so that's impulse. Now we're looking at the conservation of linear momentum. So if we go back to the impulse momentum theorem, if the average force exerted on an object is 0, if this is 0, then the change in momentum is 0. So the conservation, I'm just going to write momentum. It states that if the net external force, I'm going to say external force, that means forces outside of the system. If net external force equals 0 on a system, then the total momentum of the system is conserved, which in physics, whenever something is conserved, it means it remains constant. So if the net external force on a system is equal to 0, then the total momentum of that system will remain unchanged. It will remain constant. And whenever that happens, we say that the momentum is conserved. Alright, so I wrote system. The application of this idea of conservation of momentum is really useful when you're looking at two or more objects that are interacting with each other in some way. Alright. Now if I like to say look at two balls colliding with each other. Alright, I'm going to erase this. Let's say we have ball A and it has a mass ma, has a velocity va in this direction. Then we have ball mb, has a velocity vb in that direction. Alright? Now, the momentum before the system. Now, now that we're going to look at collisions, whenever I do a P, that means before. I'm going to denote after a collision as P prime. This is total momentum before collision. P prime is total momentum after collision. Okay? Now, the system is ball A and ball B. So the total momentum before the system, before the collision, is equal to the momentum of ball A plus the momentum of ball B, which equals mass times the velocity of ball A plus the mass of ball B times the velocity of ball B. That's the total momentum of the system before the collision. It's the sum of the momentum. Now, momentum is a vector quantity, remember? So if we say this is a positive x direction, ball A has a positive momentum, ball B has a negative momentum. So whenever we add their momentums together, they're actually going to cancel each other out to some extent. If say, the mass of ball A and the mass of ball B are equivalent and they both have the same speed, then the total momentum of the system is actually 0 because they have equal and opposite momentums. So it is possible for two objects, for the system to have objects moving, but the total momentum of the system be 0 if one object has a positive momentum and the other object has a momentum with the same magnitude but the opposite direction, so negative, and they cancel each other out. That's possible. All right? But this, in general, this is the total momentum of the system before the collision. Now they collide. What happens? Whenever they collide, they're in contact with each other for some period of time. And while in contact, ball A exerts a force on ball B. This is the force of ball A on B. And ball B exerts a force on ball A. This is the force of ball B on ball A. Now the change in momentum of ball A is going to be equal to the force of ball B on ball A times the amount of time that they're in contact with each other, right? This is the change in momentum on ball A is equal to the impulse that ball A experiences, which is the force that ball B exerts on ball A multiplied by the amount of time that that force is exerted. Now, the impulse that ball B experiences is equal to the force of ball A on ball B multiplied by the amount of time they're in contact with each other. Alright, so the change in momentum that ball B experiences is equal to the impulse it experiences, which is the force that ball A exerts on ball B multiplied by the amount of time that that force is applied, the amount of time that the balls are in contact with each other. Now Newton's third law tells us that the forces that ball A and ball B exert on each other are equal magnitude but opposite in direction. So we could rewrite the momentum, say, of one of these, say, momentum of ball, the change momentum of ball B. We can rewrite this as negative the force of ball B on ball A. You can substitute the force of A on B and with this times delta T, and you'll see that this is just a negative of that. So the change in momentum of ball A is equal to the negative change in momentum of ball B. So the total change in momentum of the system is equal to the change in momentum of ball A plus the change in momentum of ball B. But since the change in momentum of ball A is equal to they cancel each other out. So the total change in momentum of the system is equal to 0. Why? Because both ball A and ball B exert equal and opposite impulses on each other. They're in contact at the same amount of time. They exert the forces on each other for the same amount of time, and they exert equal and opposite forces. So the impulse that ball A imparts on ball B, and therefore changes ball B's momentum, is equal and opposite to the impulse that ball B exerts on ball A, which changes its momentum. So therefore their changes in momentum are equal magnitude but opposite in direction and cancel each other out. This is always going to happen whenever objects collide with each other because of Newton's third law. So within the system, forces exerted on objects within the system will not change the total momentum of the system by virtue of Newton's third law. It's only whenever forces outside the system, external to the system, act on it, will the total momentum of the system change. So something else, if I would take my finger and push ball A, then my finger, that's an external force. That's outside the system of ball A and ball B. That's going to change the momentum. Right? Where if we just look at the system of ball A and ball B, the momentum is not going to change. It's going to be conserved. Now there's a lot of applications that we can use this conservation of momentum. And the most common and popular application is propulsion. Right? You ever wonder how do objects move, right? Conservation of momentum. How do objects move? How do airplanes, boats, rockets, even in space, how do they move? It's a conservation of momentum. You think about an airplane propeller, right? I don't know how many blades an airplane propeller has. I'm just trying. As it spins, what does it do? The airplane propeller, it pushes, just like a fan pushes air in the direction. That's all an airplane propeller is a fan. So if the airplane propeller wants to propel the plane in this direction, then the airplane propeller has to spin in a way that it forces air in this direction. So it gives the air a velocity in this direction. Now the air has mass, right? Because it's atoms, it's molecules, it has mass. So the air is given a momentum in this direction. Getting ahead of myself. Before you turn the propeller on, the airplane's sitting there, the air is sitting there, the total momentum of the system is 0. If the propeller turns on, right, it starts spinning, it starts blowing air that way. So now the momentum of the air, and let's say if this is the positive x direction, is less than 0. It's not 0. It's some negative number, right? It's in this direction. The air has momentum in this direction. Now the system is the airplane in the air. Nothing else has exerted a force on the air or the airplane. The airplane exerts a force on the air, pushing the air that way, giving the air a momentum that way. Whenever the propeller pushes the air that way, at the same time, the air is pushing back this way with an equal and opposite force. And that force accelerates the propeller, which is attached to the airplane, in this direction, giving the plane a velocity in this direction. And so the plane develops a positive momentum. And the sum of the momentum of the air plus the momentum of the plane have to equal 0. Because the total momentum of the system is equal to 0. Before they started interacting with each other, there was no momentum. Everything was at rest. The airplane, through the propeller, starts pushing air that way, giving it a momentum in this direction. In return, the air starts pushing the airplane this way, giving it a momentum in that direction, so that the total momentum of the system remains constant, equal to 0. Now, the plane is much more massive than the air, right? That means that the air's velocity has to be much greater than the plane's velocity, because the plane has a very large mass. And for that to equal the change in momentum of the air has such a small mass, air has to be given very large momentum. No, sorry, very large velocity. But, you know, if you want to go even faster, you've got to push the air even faster. So that's how a propeller works on a boat, right? The propeller spins, it pushes water that way, and in return the water pushes back, and it propels the boat forward. In space, right, space is a vacuum, so there's nothing to push against, right? You can't have a propeller turn and push a fluid that way so that the fluid pushes you forward and propels you forward. So what you have to do is you have to have compressed air or some sort of fuel to burn. And if you have compressed air and if you open a valve, the pressure pushes the air out, and so the air develops. So let me say, if you're just at rest, you and this tank of compressed air. And then if you open a valve and allow the compressed air to escape, it develops a velocity in that direction. It has a mass and a velocity in that direction, so the air develops a momentum in that direction. In order for momentum to be conserved, your body develops a momentum in this direction. In the opposite direction is the air momentum. And so that's how you can propel yourself in space, right? By having some compressed air and allowing it to escape in a certain direction, you'll develop a momentum in the opposite direction. So the conservation of momentum is how propulsion works. You propel yourself by giving a fluid you're in, or a fluid you're in case of air or water, of momentum in one direction, and therefore you develop a momentum in the opposite direction. And if you're in space, you allow compressed air to escape in one direction, so it develops a momentum in one direction, so you develop momentum in the other direction. So there's a conceptual example. You're at a pond, and the pond is iced over, and you're sitting on that pond, right? It's winter time, so you're clothed in winter clothing. And let's say that this is the smoothest ice that has ever existed. So smooth that there's no friction, there's no static friction. If there's no friction, that means that you can't push against it. Because how we walk is you put your foot down on the ground, you push against the ground. So you exert a force this way in the ground. This is the force of your foot on the ground. And your foot would slide this way because you're pushing your foot this way. To prevent the sliding, the ground exerts, I should say, this force is on the ground. Your foot exerts this on the ground. And in return, the ground exerts a frictional force that way to prevent your foot from slipping this way. And so it's the friction that pushes you forward. So if there was no friction, and I push against the ground, you would just slip, right? You would do like the running in place, like you see in the cartoons. You could run, but there's no force pushing you this way, preventing you from sliding that way that propels you that way. So if there's no friction, you can't walk. You can't get up. If you try to get up, you push against this ice, you're just going to slide out, right? So you're stuck. How do you get off the ice? What we could do is your momentum is equal to 0. You're just sitting there. If you could take an article like your boot and throw your boot, give your boot a velocity in that direction, so now your boot has a momentum equal to the mass of the boot times the velocity of the boot in that direction, because before you throw your boot, the total momentum in the system was 0. Now the boot has a momentum in that direction. Your body, the momentum of the person, is the mass of the person times the velocity of the person, develops momentum in that direction in order so momentum will be conserved. So if you throw it that way, then you'll start to move this way. That's one way you can get off the ice. If you just throw an article of clothing that way, because you gave it a momentum in that direction, you will develop a momentum in this direction. How does that work? Well, in order to accelerate that boot from rest to some non-zero velocity that way, you had to exert a force on it, right? You had to throw it and exert a force on it through some period of time. So you're exerting a force on the boot for some period of time in that direction to accelerate it from rest to some velocity. Well, Newton's third law tells us that during that time, the boot was exerting an equal and opposite force on you in this direction, and therefore accelerating you in that direction, giving you a velocity in the opposite direction. And so you develop a momentum in that direction. So that's how you can get off. You just throw something. And that's propulsion, that's thrust, right? That's what a rocket engine does. It burns fuel, and it sends the exhaust out, right? The exhaust comes out with a very high speed. It has mass and high speed, and so that has to push that exhaust out, and in return, giving it a non-zero momentum downward. And in return, the exhaust pushes up on the rocket, giving it a non-zero momentum upward. And so they're pushing against each other. This is the same concept behind like a recoil. Like if you ever fire a firearm, and you shoot a firearm and it kicks back, right? Why does it kick back? Well, because when you're holding the firearm, before you fire the shell, momentum is zero. Whenever you pull the trigger, right? So the gun, the momentum is, so here's the bullet inside the gun. The momentum is zero. Whenever you fire it though, this bullet is out here. It has a mass of a bullet times a velocity of a bullet. So the momentum is in this direction. So in order for momentum to be conserved, the gun develops a momentum in this direction for it to be conserved, and that's the kickback. All right. So so it's the conservation of momentum that applies. That's what we typically call like recoil. That's conservation of momentum. So if you ever watch a movie where someone is holding like a gun or something, and then they fire it, and they stand in place and they fire it, right? Nothing happens to them. Like they might give back. But whenever it hits someone and they go flying back, well, they're saying that the projectile that was shot, its momentum is transferred into that person, and then that person goes flying. If that was the case, then if there was that much momentum involved, then the person that shot it would go flying back too, right, in the opposite direction. So the person that shot it, they'd fly back this way, just like the person that whoever gets hit by it goes flying this way. This person can't get hit by it and fly this way, and the person that shoots it just stay in place, right? Momentum is not being conserved. And so that completely violates the laws of physics. Those scenes in like science fiction movies or action movies or whatever, right? If it's something big like that, like a cannon, right? You ever see them in those movies, like a Civil War movie or something, where they fire a cannon? They put the cannon on wheels, not only to move it, but whenever it fires, it's able to roll backward, right? Roll backward. And sometimes on ships, mainly, if you see like movies with pirates and stuff, the cannons up the side of the boat, they'd be on wheels, but the track would be on an incline. So whenever it shoots, it would have to roll up an incline, so it doesn't roll as far, because then gravity, while it's rolling up, gravity's pulling it back down. So if it fires, the conservation of momentum says, oh, the cannonball has a momentum this way, so the cannon develops a momentum this way, but it rolls up that track and then it comes back down. Right, so that momentum, you can't have a huge change in momentum of a person and have no change in momentum of the person that shot it, right? It has to be the same, right? Momentum has to be conserved. So conservation of momentum applies to collisions, for propulsion, and recoil. And another example is whenever two objects collide and they stick together. So let's say there's a sled. It has a mass sled. And there's a person. And they're running, right? It's winter time. They're running, and this person has a mass mp, and they're running with a velocity vp. So their momentum, so the momentum before is the mass of the person times the velocity of the person. And this sled's at rest. The person then jumps on the sled. And together, they move with some velocity. What velocity do they move at? Well, before, the total momentum of the system was just the momentum of the person, because the sled has zero momentum. Now, the momentum afterwards is the mass of the person multiplied by whatever speed you're traveling at, plus the mass of the sled multiplied, well, we're sliding together so it's the same speed. You can factor out the velocity. You get mass of the person plus the mass of the sled, so it's the combined mass times the velocity which they move together with. And assuming that there's no friction, or even if there's friction, if we just look at their velocity at the moment that the person jumps on the sled and starts sliding, we can set the momentum before equal to the momentum after they collided. So the mass of the person times the velocity of the person equals the mass of the person plus the mass of the sled multiplied by the velocity they move at together. And you can find that velocity by dividing both sides by the mass. Right? You can see it's going to be less than the velocity of the person, right? Because this number is bigger than that number, because this is the mass of the person plus the mass of the sled. And so because this is bigger than that, this quotient is going to be less than 1. Multiply this by a number less than 1, you're going to get a smaller number. So the velocity they move together, v, has to be less than the velocity of the person. Which makes sense because now more mass is moving. In order to have the same momentum, it can't be moving with the same velocity. It has to be moving with the smaller velocity in order to have the same amount of momentum, because now there's more mass moving. But what really happens is that person jumps on the sled, they transfer some of their momentum into the sled, so that now that they're moving together. And so the person has to slow down in order to transfer some momentum to that sled. All right, so that's the conservation of linear momentum. We can use it to solve problems of collisions or propulsion. All right, and so we're going to look at some example problems where we just calculate momentum. We look at impulse, and then we'll also look at some problems where we use the conservation of momentum. And so that concludes this lecture. Thank you very much.